Okay, welcome back to our series on statistics. And this week, we're going to be talking about a one-way ANOVA. A one-way ANOVA is used when you are comparing the means of three or more groups or conditions. And it has to be that we're looking at interval or ratio data. Last lecture, we talked about the independent samples t-tests. And that was when you were comparing the difference between two means or two groups. So the difference between the one-way ANOVA and independent samples t-test is in how many groups you're comparing. Now, what's interesting, and I'm going to say this a little bit later, is that in theory, you could run a one-way ANOVA for two groups similar to the independent groups or independent samples t-test, right? But it's overkill. Now, mathematicians have found if you did that, the value of F, the F value, which is the product of the ANOVA calculation, would be equal to your T value squared. So T squared is always equal to F. But as I said, you wouldn't really run a one-way ANOVA if you had two groups. It's allowed, but it's not typically what people do. So let me get into the lesson, and I'm going to pull up my slides and we will continue, right? All right, so here we are, the one-way ANOVA. Now, when we talk about a one-way ANOVA, we can do this for all kinds of things, truth be told, but I'm going to give you an example of a scenario where you might use a one-way ANOVA. Imagine you are trying to determine whether three different kinds of therapy models worked to alleviate the symptoms of phobias. Now, you could compare the different models of therapy against one another to see if one is significantly better than the rest in the treatment of phobias. So in this scenario, let's say we had general counseling, maybe this is psychoeducation or whatnot about phobias. And we compare that against something like systematic desensitization, which is a form of an exposure therapy where you gradually introduce the person to whatever the feared issue was, and slowly bring them closer and closer to their fear. And then we could compare that against rational emotive behavioral therapy. And rational emotive behavioral therapy is the belief that our thoughts and our emotions drive our behaviors. So this is more of a form of a cognitive behavioral therapy, whereas systematic desensitization, being an exposure therapy, is more of a pure behavioral intervention. So that's the scenario. We're going to come back to it. So why not run a whole bunch of t-tests where we compare group 1 against 2, 1 against 3, or 2 against 3, right? So in this case, if we ran 3 t-tests, we would have a problem. What is the problem? As scientists, we accept the error or alpha as 0.05. So we allow up to 5% error in each study. Now we can make that alpha or error level of significance lower if we wanted. But in this case, if we ran 3 tests with an alpha of 0.05, then putting that together, we might have an alpha of 0.15, right? So, and if we ran 20 of these t-tests, we would wind up with almost a guarantee that at least one of our conclusions would have been a type 1 error. So the beauty of a one-way ANOVA is that we can compare all the groups against one another while maintaining that alpha of 0.05. So it reduces the risk of a type 1 error. Doing the t-test, it increases the risk of a type 1 error. And you might remember I defined a type 1 error as rejecting the null hypothesis, when the null hypothesis was actually true. So why is it called an ANOVA? Well, the ANOVA is an abbreviation. The full term is analysis of variance. That's the full term. And I underlined where we got the ANOVA, ANOVA from, right? So as I said, as an introduction to this slideshow, we are typically using an ANOVA when we have 3 or more means that we're comparing. So the null hypothesis, as I defined the null hypothesis in previous lessons, that is to say there are no statistically significant differences between the groups. And if there are differences, it's due to error. So in this case, the null hypothesis would be expressed as mu1 is equal to mu2, which is equal to mu3, right? So if they're equal, there are no differences. The alternative hypothesis or research hypothesis is mu1 is not equal to mu2, which is not equal to mu3. So that would be saying there are real differences between the groups, and it's due to our manipulation. So let's understand the logic of the ANOVA. When we look at a one-way ANOVA, we are going to get within group variance and we're going to get between group variance. When we think of within group variance, this is how much scores differ from one another within the same group. So if you were in a specific treatment modality and you're differing within that group, we would expect that that error is something other than the treatment. I give an example, and it's not a perfect example, but imagine I was doing a personality test. And I gave you a personality test today, and then I gave you a personality test in a month, and then 3 months in a year. Would I expect your personality to differ significantly at point A, B, C, and D? The answer is no, because you're the same person. And there might be minor differences, but I wouldn't expect you to have a full personality overhaul. And if you did, that likely reflects itself as a personality disorder, because for most people, our personality is relatively stable. So within group variance is always considered error or error variance, right? So whereas between groups variance, that's different interventions, I would expect you to have different responses to the general counseling versus the exposure therapy versus the rational motive behavioral therapy. They're different interventions. So I would expect there to be different responses to the intervention. The analogy, if I keep the same analogy going, if I gave you a personality test and I took a personality test and we compared the results, would we expect there to be differences between your score and my score? The answer is obviously yes, because no two people are identical. Even identical twins are not identical. So if we're doing different therapy interventions, we would expect you to respond to those interventions differently. And we compare the average, right? So the average of each group. So another aspect of the logic is the null hypothesis would state that there are no difference between the groups. So when we compare the averages for group 1 against group 2 against group 3, the null hypothesis would basically say that all of these bell curves are overlapping. Well, what happens with between groups variances, there might be differences between them. And the farther these differences are, the larger the between groups variances, sorry, that's my cat. The larger the between groups variances are, the more likely they are coming from different populations, or what we would say there are real differences between the groups, or we can feel more confident rejecting the null. So here is a breakdown. So between groups variance, it could be due to our treatment, or it could be due to error. But within groups variance is always error, right? So if the null hypothesis were true, there is no treatment variance, right? And the ratio of the two would be approximately 1.0. So here is a conceptual formula, and I'm going to get into the calculation shortly, but the conceptual formula for ANOVA F is equal to between groups variance divided by within groups variance. So between groups variance is the numerator, which I said could be treatment variance or error variance. Within groups variance, which is the denominator, is always error. All right. So now let's get into our pieces of the formula we need. The first thing we're going to need is we are going to have to calculate 3 aspects of sum of squares. So this is getting some level of variance between the groups, within the groups, and the overall variance. So sum of squares total is expressed in different ways. So it's expressed as the sum of x minus x bar g squared. That's more of a definitional formula. Or it's expressed as the sum of x squared column, which I'm going to do both of these, minus the total number of participants times the grand mean, right, squared. So there, that would be more of a computational formula. We have the sum of squares between groups. So the sum of squares between groups is the sum of n times an individual mean subtracted by the group mean squared, or n times the sum of the individual mean minus the grand mean squared. So that you could see that it's written n times or the sum of n times, right? It's expressed the same way. Now, sum of squares within groups is expressed as the sum of x minus x bar 1, and we just do that for all of them, squared, and then we add them all up. But truth is, because we know that the sum of squares total is the sum of squares between groups plus the sum of squares within groups, if we had the sum of squares total and the sum of squares between groups, we could just do SST minus SSB gives us SSW. And I'm going to write all the formulas on the board as I go. Now, degrees of freedom, you recall, is the number of cases that are allowed to vary from a constant. So in the case of degrees of freedom between groups, these are the number of groups minus 1. Degrees of freedom within groups is the total number of participants in the study minus k, which is the number of groups. And then the degrees of freedom total is the total number of participants minus 1. Mean squares, the mean squares formula is the sum of squares of a given aspect divided by its respective degrees of freedom. So mean squares between groups would be the sum of squares between groups divided by the degrees of freedom between groups. Mean squares within groups, sum of squares within groups divided by degrees of freedom within groups. And then the F value is dividing mean squares between relative to mean squares within. Now, when comparing the F ratio for an F distribution, we do wind up getting somewhat of a positively skewed distribution. And unlike previous lessons where we only needed one number for degrees of freedom, when it comes to the ANOVA, we need 2 sets of numbers, 2 sets of degrees of freedom. So we need the degrees of freedom between groups, and we need the degrees of freedom within groups. And that's how we're going to determine our critical value. So I'm going to stop the share here, then set up the board, and we'll reconvene, and then I'm going to come back to this example. So let me stop my share and then pause the video, and then I'm going to come back with the board all set up. Okay, here we are. So on this board, I just put a series of groups. So this is group 1, group 2, group 3, group 4, group 5. This is a different demo relative to what we had on the slides. So we have 5 different groups. And what you'll notice is I just put scores in each of the groups. And I have symbols here that I'm going to take you through. So the first symbol that's relevant is x minus x bar g squared. And that goes across for all of them. Then I have symbols for the sum, n1, x bar 1, and I do it for all the groups. And then at the end, I have a whole bunch of symbols. Then I have my formulas for the sum of squares. So we're going to, because the board is small, we're going to work through each of these formulas. Then I'm going to erase this, and then I'm going to go back and we're going to do degrees of freedom and mean squares and all of that. So let's start by adding up our columns. So if we add up this column, we should get a number that is 71, right? You can fact check me. Now, how many participants? N1 is how many participants are in group 1? 1, 2, 3, 4, 5. So N1 is 5. And then when I get the mean, in order to get the mean, I just say 71 divided by 5. And what I get is a mean score of 14.2, right? So now let's do that for the second one. If I add all these up, I'm going to get a sum that is 66. And when I do that, what I'm going to do now is add up the number of participants, 1, 2, 3, 4, 5. So now what's 66 divided by 5? That's going to give me a mean of 13.2. No problem. I'm going to keep moving across. I'm going to add up column 3. When I add up column 3, the total comes to 62. Still count my number of participants. I have 5 in that group as well. Now there's going to be 5 in all groups for this demo. Now what's 62 divided by 5? That should give us a mean of 12.4. All right, so 12.4, I'm going to make that more legible. The next one we add up, group 4, we get, again, I guess if we add that up, hold on, let me just double check. Yeah, we get 66 again. And then the total number of participants is 5 again. So that's going to be the same as before, 13.2. Okay. And then we have one more column to add up. And then I think we can start working our way on the symbols here. So we add up the last column, and then we're going to get something that looks like this. 60. Then that's going to be 5. If we divide 60 divided by 5, we get a mean score of 12. Now, I put a bunch of symbols over here as well. Ignore the x squared column because I'm going to show you this whole problem using a computational formula afterwards. But I'm going to do this because these 3 symbols correspond to all of these. So if I were to add up all of my x columns, 71 plus 66 plus 62 plus 66 plus 60, the sum of my x column would be 325. So if you're wondering, how did I get this? I added 60 plus 66 plus 62, 66, and then 71. Now my NT stands for N total. 5 plus 5 plus 5 plus 5 plus 5. There were 5 participants in each group, and there were 5 groups. So that becomes 25. So now, to get the grand mean, we could add all of these up and divide by 5, or we could just do 325 divided by 25. And if we did that, we would get a grand mean of 13. Now that's important because we're working our way through it. Now we had to do all of that to get the grand mean, right? Now we're ready to calculate sum of squares total. Now the sum of squares total is the sum of the x minus x bar g squared column. So I'm going to do it in the column here. I'm going to work through my columns. And if I were to do the first one, x, which is 16, minus x bar g is 13. 16 minus 13 would be 3 squared, or 9. Does that make sense? So 16 is the individual score minus the grand mean, which is what's in parentheses. We get 16 minus 13 is 3, and we have the squared sign, which gives us 9. The next one would be 3 squared again, which gives us 9. 14 minus 13 would be 1 squared, which gives us 1. 13 minus 13 would be 0 squared, which gives us 0. And then 12 minus 13 would be negative 1 squared, which gives us 1. Now, if we add up these numbers, what's 9 plus 9 plus 1 plus 1? We're going to get 20. Okay, so in this column, we have 20. Great. We're going to do the same thing for our second set of numbers. 16 minus 13 squared is 3 squared, or 9. 14 minus 13 is 1 squared, which is 1. This is 0 squared, which is 0. 0 squared again, which is 0. 12 minus 13, we get negative 1 squared, which becomes 1. So if we add that up, what do we get? So 9, let me just make sure. Hold on, did I put a wrong number? In my demo, I made a wrong number. I'm going to change this number out. Sorry about that. I could do it with this too, but this is 10. So if you would have added this up, you would have found that it was a mistake. It didn't come to 66. So 10, 23, 36, 50, 66. I caught a typo in my work. So 10 minus 13 is negative 3 squared, which gives us 9. So if we add this up, we're going to get 19. And we're going to keep working our way across. And I'm going to be more careful to make sure my numbers are indeed what they were supposed to be. 14, 13, 13, 10, 10. Okay, yeah, my demo looks right going forward. So 16 minus 13 again is 3 squared, or 9. 1 squared, or 1. Negative 1 squared, or 1. 10 negative 3 squared, or 9. Negative 3 squared, or 9. So now we add this up, and what do we get? We add that up, and we're going to get a number 29, right? 9 times 3 is 27, plus 2 is 20, 29. Okay, move into group 4. So if we go to group 4, again, this is 3 squared, or 9, 1 squared, or 1, minus 1 squared, or 1, minus 1 squared, or 1, minus 1 squared, or 1. We add that up, and we're going to get 13. Okay. Now, we have one more column, and then we're going to be able to fill in this number here. So 14 minus 13 is 1 squared, or 1. 0 squared, or 0. 0 squared, or 0. See, I'm just doing the subtraction as I was doing. Minus 3 squared, or 9. Minus 3 squared, or 9. Add that up. So when we add that up, we get 19. Now, let's take this formula here. The sum of squares total is equal to the sum of x minus x bar g. So I have to take all these numbers that I had to add them up. So I already added the column, so that's going to be expressed as 20 plus 19 plus 29 plus 13 plus 19. So if we add these 5 numbers, 20 plus 19, 39, 59, and then 9 is 68, 78, 81. This brings us to 100. Now I'm doing mental math, but I encourage you to use your calculator. So the sum of squares total is going to be 100, right? So that's pretty easy. Now, the next thing we're going to do is do the sum of squares between groups. Now, again, I'm going to show you how this is expressed and work you through it. Sum of squares between groups is a sum of the individual n times the individual mean minus the grand mean squared. Now I do dot, dot, dot. I did 2, 3 because the standard ANOVA has 3 groups, but I did dot, dot, dot to let you know you would do it for all of the groups you have. And in fact, in our case, we would have a total of 5 groups, right? So let's express this. So we have 5 times the individual mean, 14.2, minus the grand mean of 13 squared, plus 5 times our second mean was 13.2 minus 13 squared, plus 5 times our third one, our third one is 12.4 minus 13 squared, plus 5 times our fourth mean, which was 13.2 minus, sorry about that. All right, so this should be 5 times 13.2 minus 13 squared, plus our last one, which is 5 times 12 minus 13 squared. So if we work through this, you are going to get a number that looks like this: 5 times 1.2 squared plus 5 times 0.2 squared plus 5 times negative 0.6 squared plus 0.2, 5 times 0.2 squared plus 5 times negative 1 squared. So, all right, this is a plus sign. Okay, so if we do that, what is 1.2 squared, right? And we multiply that by 5, this is going to be 7.2 plus 0.2 squared, and then we multiply by 5, you're going to get 0.2 plus the third one is 0.6 squared times 5. You are going to get 1.8 plus 0.2 squared times 5, which is going to get again 0.2 plus negative 1 squared, which is 1 times 5 is 5. So this is quite messy, but the principle's the same. We take each individual mean, subtract it by the grand mean, square it, then multiply it by its individual numbers. So now we just add these numbers up. What's 7.2 plus 0.2 plus 1.8 plus 0.2 plus 0.5? If we add that up, we should get a total of 14.4. So now I've calculated my degrees of freedom between, my sum of squares between groups. All right, so the last thing I need to do is calculate this. Now we do have a formula for this, but I'm going to use a simplified formula by saying 100 minus 14.4. And what does that give us if we did that? We should get a score of 85.6. Now, I said the sum of squares total should equal to the sum of squares between groups plus the sum of squares within groups. So does 14.4 plus 85.6 equal 100? Yes, it does. So now let's move to our degrees of freedom. So our degrees of freedom between groups is k minus 1. So k is the number of groups. How many groups do I have? 1, 2, 3, 4, 5, right? So I have 5 groups, right? So degrees of freedom, 5 minus 1 gives me 4. Okay, so I put 4 there. Now, degrees of freedom within groups is n total minus k. So n total was 25 minus 5 groups gives us 20. Now, what is 4 plus 20? That's 24. Now you can fact check yourself to see if you made a mistake, because the degrees of freedom total is nt minus 1, which is 25 minus 1, which gives us 24. So far we have plugged in our summary table 6 of the scores. It gets easier from this point forward. The next thing we need to do is calculate mean scores. If you don't mind, I'm going to erase what I have and then create space for our mean scores. And I'm going to redo this whole thing using a whole set of numbers too, which is going to be cool. I think you're going to like it. So mean squares between groups is SSB over DFB. Now, if we look at the table, all that is just dividing these two numbers. So if we were to take 14.4 and divide that by 4, what do we get? 14.4 divided by 4 gives us 3.6. 3.6. Okay. So now the next thing we need to do is calculate our mean squares within groups. SSW divided by DFW, which gives us 85.6 over 20, right? That's just dividing across here. What do we get? 85.6 divided by 20 gives us 4.28. Okay. Now, the F value is MSB over MSW. So now that's dividing this way, or 3.6 divided by 4.28. Let's see what we come up with. 3.6 divided by 4.28 gives us 0.841. Okay, so here was our first calculation. So we did all of our processes using a definitional formula. The last thing we need to do is to work it through our 8 steps, right? So step 1 was to establish our alpha, 0.05. Step 2 is the null and alternative hypothesis. Now, our null hypothesis, we have 5 groups in this time. So we say mu1 equals mu2 equals mu3 equals mu4 equals mu5. The alternative hypothesis is mu1 is not equal to mu2, which is not equal to mu3, which is not equal to mu4, which is not equal to mu5. Now, 3, we're going to say it's two-tailed. 4, we need our critical value. No, we need our degrees of freedom. So in this case, we need DFB, comma, DFW. So what was our DFB? 4, comma, 20. Now, step 5 is to get the critical value, okay? For that, I'm going to need to go in the back of my book, and we're going to find our critical value that way. So let me get my book out. And at this point, you need to go to the table that says critical value of F. Now, I'm going to show you this table, but it's very important to know, I don't know if you could see this, you go across, then down. So what are my degrees of freedom between groups? I go to 4 and go to 4 across, then go down to 20. Now, down this page, it goes only to 13. So what am I going to have to do? I'm going to have to turn the page, and then, oh, I found it. So we go across to 4, go down to 20, and I don't know if you can see, but I boxed it. It's 2.87 is our critical value. Now you'll notice there are 2 numbers. The bottom number, which is bold, is an alpha of 0.01. The regular font is 0.05, which was our alpha. So here we are with a critical value of 2.87. Step 6 was to calculate our F test, although we always do that out front. So this would be 0.841. Step 7 is to make a decision. Now, what decision do we have to make? We have to make the decision whether we're going to accept the null or reject the null. So how do we do this? This is the same as before. We compare our calculation score relative to our critical value. And what we find when we do that is that our observed score is less than the critical value. Now, we would only reject the null if our calculated score was equal to or greater than our critical value. So in this case, we accept the null, and then we have to interpret that. And I'm going to give you words to interpret this. Now, I didn't tell you what each group was, so that makes it a little bit easier. Using a one-way analysis of variance, we found no statistically significant differences between the group means. I'll say that again. Using an independent samples t-test, we found no statistically significant differences between the means. Now, what I'm going to do now is I'm going to pause this and I'm going to reset the board. I'm going to keep this table here, but I'm going to erase all of this and I'm going to put new calculations for our sum of squares. So if you humor me, I'm going to pause this and then reset. Okay, so here I set up the board with computational formulas to get our numbers. Now I left the numbers here because the truth is it doesn't matter whether you use the definitional formula or the computational formula. You should come to the same final numbers regardless. So humor me. Now I have x squared columns instead of x minus x bar g, and I'm going to try and fill up that number over here. So what's 16 squared? That is 256. Again, 256. 14 squared is 196. 13 squared is 169. And 12 squared is 144. Now, if we add up this column, what do we get? We get a sum of 1,021. Great. Now let's move to the second column. Again, 16 squared is 256. 14 squared is 196. 13 squared is 169. 13 squared is 169. Again, we're just taking the number and squaring it. And 10 squared is 100. Okay. If we add that column up, we're going to get 890. Great. Let's move to the third column. Now we have, again, 256, 196, 144, 100, and 100, right? Add that column up, we're going to get 796. Now, moving to our fourth column, if we could, we're going to do, again, squaring 16, 256. 14 squared is 196. And we have 144, 144, and 144. So if we add that up, we should get 884. So that's 884. Okay. So we're now up to our last column. And we're going to add these up. 14 squared, 196. 13 squared was 169. 169 again. 100 and 100 again. Add that up. If you add that up, you get 734. Okay, so now you see this number, the sum of x squared? What is the sum of x squared? We have to add 1,021 plus 890 plus 796 plus 884 plus 734. Now, if we add all of that up, what do we get? I'm going to do that now just to make sure that I get it right. We're going to do 1,021 plus 890 plus 796 plus 884 plus 734. And that's going to give us a number of 4325. So let me do 4325. here. Okay, so now I have all the numbers I need to calculate my sum of squares total and my sum of squares between groups. So this formula for sum of squares total, the computation is the sum of x square column, right? What is that? 4325 minus the sum of the x column, 325, squared over n total. And total was 25. Okay, so we have 4325 minus, what's 325 squared? 325 squared is 105,625 over 25. Now, at this point, we can do 4325. And now let's do this last part. 105,625 divided by 25. We get 4325 minus 4225. Now, if I were to ask you what 4,325 minus 4,225 is, that's easy, right? Easy math, it's 100. So whether we did the old formula of x minus x bar square or the computational formula, we're going to get to the same 100 number, right? So in this case, using this formula, we get 100. Now humor me. Here's another cool formula. So n total, 25. This is a real shortcut. Times x bar g, 13 squared. So if we do that, 25 times 169, right? We are going to get 25 times 169. We're going to get 4225, right? Interesting. 4225 minus 4325 gets us the same 100, right? So is that clear? So if we take this and subtract it from the x minus x bar square, we still get the same thing of, and I'm going to write this differently. So it's the sum of x square column minus nt, just so we're clear, times x bar g squared, right? So we're going to get something that looks like this. 4325 minus 4225 equals 100, regardless which formula we use. Now let's get into the sum of squares between groups. Now, if we do the sum of squares between groups, we're going to have to do this manually. What was the sum of x1? 71, right? 71, actually, I don't like the way I wrote that. 71 squared over n1. What was n1? 5 plus sum of x squared. This is now, pardon me, sum of x1 squared divided by n, x bar, I'll say that again. The sum of the x column 2 divided by its number of participants, 66 over 5 squared plus 62 squared over 5 plus 66 squared over 5 plus, what was the last one? 60. squared over 5 minus the sum of x, and this should be squared, right? So we take minus 325 squared over nt, which is 25. So now let's start to plug in these numbers. If I were to do 71 squared, squared, divided by 5, I'm going to get something that looks like 1008.2. Okay, so let's put 1008.2 here, plus, because I'm working these formulas, now we're going to do 66 squared divided by 5. We're going to get 871.2 plus 62 squared divided by 5 gives us 768.8 plus 66 squared again divided by 5 gives us 871.2. And lastly, 60 squared divided by 5. 60 squared divided by 5 gives us 720. And then we subtract that by 325 squared divided by 25. Now, hold on, let me just double check that again. 325 squared divided by 25 gives us minus 4225. Now, you should get used to seeing that 4225 because it was here as well, right? So, okay, now let's add everything up. We get 1008.2 plus 871.2 plus 768.8 plus 860, what? Almost made a mistake. 871.2 plus, I think that was 720. Let me just double check that. I think that was 720 plus 720, right? If I do that, I get a number that is 4239.4 minus 4225. What do we get? 14.4. So, sorry for the typos. I like to catch my mistakes. But if we took the sum of the x column squared divided by its number of participants, added it all up, and then subtracted by the sum of the x total from the whole study divided by the total number of participants, we get 14.4. So this 100, which was already written, this 14.4, which was already written, notice it didn't matter. I changed the board, used a different formula, and I got to the same place. Now, the rest of this I don't need to do because they don't have any different formulas. So that is how you would calculate a one-way ANOVA by hand. So now I'm going to go back into the lecture and I'm going to press pause here and I'm going to pull up the slides again. All right, so that was the demo of how to calculate it by hands, but you're always going to have an ANOVA summary table. So let's go back to the example from our slideshow. We were asking whether general counseling, systematic desensitization, or rational emotive behavioral therapy differed significantly on treatment outcomes. So we're going to suggest that the lower number is a reduction in phobias. So let's see, if we were to run this calculation, we could actually come up with this summary table. And in this particular case, our F value is 16.33. Now I'm going to go into the back of the book to see what the critical value would have been. So let me go in the back of the book, and I go across to 2 and down to 42, and I match it up. So I actually have pre-written it. I don't know if you can see the arrows, but if you see the arrows, you're going to see that it comes to 3.22, or if I wanted a 0.01 alpha, it would come to 5.15. So it's clear our F value of 16.33 is greater than our critical value. Thus, in this case, we would reject the null. That would have been our decision here, which would suggest that using a one-way analysis of variance, we found statistically significant differences in treatment outcomes, whether you used general counseling, systematic desensitization, or rational emotive behavioral therapy. So that would be how we would do it, right? We would calculate that, and sure enough, there are differences. Now, which groups differ significantly from the rest? Well, for that, we can't answer by just looking at the summary table. For example, if I were to ask you, did the rational emotive therapy group differ significantly from the general counseling group? You might say, well, yeah, those are the two extremes, but we have a process to determine that. How about systematic desensitization to rational emotive behavioral therapy? You're like, well, the mean is just 1, but maybe that 1 point difference, depending on sample size and a lot of other things, that could still be statistically significant. So if we have a significant general model, so if this summary table, we find statistical significance, we need to do what's called a pairwise comparison or a post hoc test. Eyeballing the data above is not enough to determine whether we have significant differences. So we would need a post hoc analysis to determine that. All right. Now, I said this to you earlier before I even put up the slides. I said, if you had a 2-group case where you ran a one-way ANOVA, your F value is always equal to your T value square. So if that's being said, look at all the formulas. We did 9 formulas to get to the F value, whereas the independent samples t-test, it was 1 formula. So most people would not run a one-way ANOVA for a 2-group case, but it's just mathematicians found it lawful so that this became the case where F value is equal to T value squared. Now, we also talked about pooled variance in our lecture on t-tests. For the ANOVA, our mean squares is our new label for pooled variance. So that's what our mean squares are, pooled variance. Now, what is a pooled variance? It's a weighted average of the variances for all of the groups. Now, here is a simplified formula for an F value for equal sample sizes. So if you take n times the standard error of the mean, right, and divide that by the sum of the variances for the individual groups divided by the number of groups, you could calculate F value. People don't use this formula. People use the formulas that I've given you. Now, effect size. Effect size, we want to know, because even if you have a finding that's statistically significant, we want to know how strong is that effect. So we have calculations of effect size for virtually all of our statistics. So we can find effect size using any one of these formulas, right? So in this case, let's use the example of therapy. we would want to know how much variability in phobia reduction can be explained by treatment modality. So we're trying to figure out how much of the variability of X can be explained by Y. You don't need to know these formulas. You're not going to be tested on them. You need to know effect size conceptually. How much of the variability in X can be explained by Y? So in the case of the treatment modality, how much of the reduction in phobic responses can be explained by treatment modality? Now, what are some underlying assumptions when it comes to the one-way ANOVA? Well, the assumption is that each of the groups are independent from one another. So if you were in the general counseling group, you would be separate or independent from a person in the systematic desensitization group, and so forth. We also assume equal variance or homogeneity variance. We said that we do that with the t-test as well. We expect there to be roughly similar variance scores. We don't want to have significant differences in our variances. We also assume that each of the populations are normally distributed, no different than a t-test. Now, I said to you that the general model will tell you that you found something that's statistically significant, but it will not tell you where that significance occurred. It will not tell you which groups differ from one another. So you could do a priori with a hypothesis to compare a couple groups. You might have had a hypothesis about how it would go. Or you could do what's called a post hoc analysis. If you're using SPSS, it's as simple as selecting post hoc and then selecting whichever one you want. And that will give you which groups differed significantly from one another. And that, my friends, is today's lesson. I know I went a little bit longer than I like to go, but hey, I showed you how to calculate the formulas in 2 different ways. So that's going to take time. So I will see you next time. Take care, everybody, and stay safe.